Hello, can people hear me? Okay, this is 10 p.m. at Beijing time and 9 a.m. in New York EST time. And welcome everyone to the 128th talk of Nice Talk. So today we are very glad to be able to invite Xingwei Qu to give us a talk about a new type of large language model, a new architecture. So the talk is called Toward Adaptive Semantic Reasoning, Architectural Innovations and Scaling Laws of Dynamic Large Concept Models. And I am today's host, Wenyue Hua. And Xingwei Qu is a PhD student at University of Manchester. His advisor is Professor Chenghua Lin, and he focused on advancing foundational capabilities and the scalability of large language models. His research investigates pre-training paradigms that enhance generalizability with a particular emphasis on data efficiency and architectural optimization. He is currently a research intern at ByteDance Seed, working on next-generation pre-training strategies to build robust foundation models that achieve superior performance at scale. And I am the host. I'm currently a senior researcher at Microsoft Research. I obtained my PhD at Rutgers University, and and previously a postdoc at Santa Barbara. Okay, let's please invite Xingwei Qu to give us this talk.
Hello everyone. It's my great honor to be here to present my recent work, which is called the Dynamic Large Concept Models, so latent reasoning in adaptive space. So before we get started, I just wanted to comparing two fundamentally different ways of thinking. So in the left-hand side is what all standard LLMs operate. So we call this as a token level models. So they are strictly token level. What they are doing is that they are doing the next token guessing game. So every tokens they keep asking a question, given the previous content. So what is the most probability of the next word? But humans does not work like that, right? So considering what I'm doing here, I'm sitting here and presenting. So I'm just not predicting the next tokens. So I'm not thinking about what the next token is this or the or are. I'm not asking my question, always asking my question, where the word come from. So instead, I'm navigating through a mental map. So I have a lot of ideas or concept in my mind, and from one concept to the next concept. Because I have this concept, the words are token just naturally flow out to match my ideas. So this is how we think. So there's a natural question. So why our human evolution favor this concept way to think? So why we do not do the next token prediction, this kind of paradigm? That's because the information density. So take an example, the theory of relativity implies time dilation. So this sentence. So you can see this diagram here. So for human, this sentence definitely have different kind of this sentence is flat. So it has peak and valleys. So some words like the, of, or theory. So all of them are the functional words, and they do not have any too much information, so which we call low density informations. And for the relativity and time dilation, we will engage some deep reasoning here, because we wanted to understand what's the meaning of relativity. So what's the relationship between the relativity and the time dilation? So we adaptively pay our attention to different kind of phrases or concept. So that's why we use concept-based reasoning, because some of the words are less density, so we do not pay too much attention, and some of them are high density, so we should pay more energy onto it. So here we got the problem. So because LLMs, standard LLMs applies uniform computation to all tokens, despite languages are non-uniform densities. So this will lead to drawbacks. The first one is that with capacity on the local predictable spans that, for example, function or words, or under-allocate computation to semantically critical transitions. So this would result as a systematically misallocation of model capacity. So how our model really works, how our model process information. So you can look at the diagram in the right hand side. So so first we use our sensor like eyes or something, or nose or something. We got the signals. This signal could be the light, could be the language, could be a lot of things, and then we use these kind of raw signals convert into a neural pattern. So after this neural pattern is processed, we format into a concept, group all of these meaningful neural pattern to a meaningful trunks. Afterwards, we reason in this kind of trunks, connecting and processing the concept, and then naturally we express. So inspired by this kind of human reasoning 4-stage pipeline, we develop a large language model pipeline. So first, we do the encoding. So for the language model, we do the encoding, process the raw tokens into a extract fine-grained local representation. So afterwards, we do the dynamic segmentation, detect semantic boundaries, and pulls all the token embeddings into the compressed concepts. So afterwards, we do quite a lot of compute on the concept reasoning. So with all of these compressed concepts, and then we reconstruct in the token level while causal cross attention. So comparing to the standard LLMs, we add these two modules here, because for the standard LLMs, they just do a encoding and decoding. So you could not distinguish what the encoding and decoding difference there. So we add these two modules to force our LLMs to thinking in a more abstract, more high-level unit. And we wanted to see if this kind of paradigm could help LLMs to improve their reasoning performance or other things. So here is the detailed architecture that shows our overview pipeline. So here is an example. So we given these 7 tokens here. So BOS token, the cat set on the mat, and then we do the encoder to get the local representation here, and each of them would be cut into different trunks. And for example, BOS token as one trunk, the cat as one trunk, Saturn as one trunk, and the matter as one trunk. And afterwards, we do the pooling to get 4 concept here. So you can see that the input sequence dimension shrinks in this kind of for this concept model. And afterwards, we use this kind of basic concept model to do the concept level reasoning, and then we got the final concept, and then we use cross attention to engage the original token embeddings and the concept that we have already reasoned to predict the final words, the period. So let's afterwards I will introduce some details about our pipelines. The first one would be the encodings. So this encoder is quite simple. It's just a standard causal transformer. So precise tokens to extract fine-grained representations. So the raw token input is x equals to xy to the xl. So L is the length of your input sequence, and then it will output a representation of H that is L times D of the token embeddings. So afterwards, we do the dynamic segmentations. So how do we actually group these of tokens into meaningful units? So when I trying to design this, I knew I want to avoid two pitfalls. The first one that I don't really want to annotate all of false corpus, so give each corpus a boundary. So because this is so expensive and it's not scalable. And the second, we didn't want to do like the other models, use a fixed stride to blindly chop the text every a few tokens. So this will break the natural flow of the meanings. So here's the question: can we make the segmentation spontaneously? So because we wanted the model itself to feel where the concept and where the next begin. So we use this kind of significant shifts to define our boundary where our boundary happens. So here is a mathematical formulation. So we got the H, which is hidden embeddings from the encoder. We use some weight to project them into the Latin space, and then we use cosine similarity to calculate the adjacent tokens semantic difference. So if two tokens are similar, so we keep them together, merge them into one trunk. If the similarity drops, so we knew we hit a boundary. So that is how we let the concept emerging naturally from data. So rather than use some supervised labeling to do that. So afterwards, let's go into the actual code. So our ultimate goal is focusing on the right-hand side. So it's the inference phase. So when we deploy this model, so we wanted to a very sharp and distinct boundary. So what we want to do that is that the model. So when a model look at a phrase or a sentence or a sequence, we want to see that the boundary is here, here, here. So see, I don't want the model give me some fuzzy probability like 0.49 or 0.551. So we need it to decisive. But as the neural network is continuous, so all model of the cosine similarity is also from the neural network outputs. So it will easily to get a very continuous number. So that's why we wanted to introduce the Bernoulli sampling with the temperature alpha to encourage the distinct correctness during the training. So for the Bernoulli, so what we want to do is that we wanted to push the probability away from the middle, so towards to the extremes. So either clear 0 or clear 1s. But with only Bernoulli sampling, yeah, it's not differentiable. So what we do is that we introduce a temperature alpha to make the distribution something like that, to make it trainable. So because we force the model to practice being sharp during the training, so when we get to inference, we can simply use hard thresholding at 0.5. And the model is already very confident, and it simply can produce some stable and reproducible concept as we wanted. So for this part is the global parser. So before we introduce the global parser, we need to first introduce the auxiliary loss. So why we use this loss? So thinking about the problem, if we only use the standard next token prediction paradigm loss, so our dynamic segmentation will fail. So why? This is because of fundamental conflict. So next token prediction hates compression. The goal of next token prediction is perfect restoration. So it wants to reconstruct the input section exactly, so with zero errors, but unavoidably compression implies loss. So to avoid this loss, so the model will naturally fight back. So it will shrink our segment size down to until one concept exactly match to tokens, because this is a safety way to guarantee the perfect reconstruction. But that defeats our purpose. So because we don't want a one-to-one mappings, we want a high-level reasoning. That's why we need a counterforce. So we introduced the auxiliary laws here. So these laws force our model to accept accept that kind of compression loss. So we will during the training we will set a target compression rate, which is called R, and then we tell if I know you wanted to keep any details, but we are not allowed. You need to compress every four tokens as a concept. So here is the details and the mathematical equation about the formula, a mathematical formula about this auxiliary loss. So where the P is as shown in the blue line, so it's the output similarity score here, and B is P bigger than 0.5. It's a hard threshold 0.1. So by using this auxiliary loss, we could help prevent our tokens we could force our models to compress the several tokens into our target one concept. So finally, I will introduce about the global parser. So look at the paradigm on the bottom right here. So if we decide that the target compression is 4, so but the real world data is not uniform, so it will go to another pitfall, is that fixed right. But we really wanted to avoid that. So what we are doing is that we feed our model some different sources, like in one batch. And so this could be the Python code, this could be the math formula and English novels. Because the Python code is extremely dense and every symbol matters. So if you compress it too much, so you break the logic. But for the English novels are low density, you can skip so half those words and you can still get the plot. So we don't want to force our model to compress everything by exactly 4 times. So that would be a disaster, as we mentioned before. So instead, we give our model some autonomy. So what we are doing is that we enforce the 4 times target compression on global average. So this could allow our model to borrow the budget from the easy text in the English novel, and spend more budget on the hard stuff like the code. So this kind of segmentation alignment would naturally align the information density from the different sources. So afterwards, we do the concept of formation. So for this part, so the tokens between the boundary are grouped together. So each of the segments is being pooling into concept vectors. So that means that we convert a long token concept sequence into a much shorter concept sequence. And then we do the concept reasoning. So the architecture is also very standard. It's a causal transformer, and there is a lot of computation happens here because our sequence is much shorter. So in this part, we could afford a deeper and wider reasoning. So finally, we decode the tokens back. So what we are doing is that we use the encoder representations that from our encoder, which is Q, and then we use the concept that we have processed here, and we do the cross attention to just got the token predicted, guided by the concepts. So here is some engineer tricks here. So about the efficiencies. So if you look at this picture, so because our concept has different lenses here, so what we will get if we're doing the causal cross attention, we will get this kind of mask that's quite irregular. So it will also changed with the length of every single tokens. So if the concept is 3 tokens, 3 tokens per concept, the attention will change. So it's different from the standard causal mask. So normally, if you wanted to run this kind of custom mask like this, your only option is to use the flex attention. But although the flex attention is flexible, it's still a little bit slower than the flash attention, so which is well optimized. So what we are doing is that we replicate the concept here, so and align them to the each queries, and then we could get a square attention mask here. So with this kind of flash attention with a simple function, pay-touch function called repeat interleave, we could get 1.73 speed up during the training phase. So here is, after introduce the whole pipeline, so I will show you during the inference phase why DLSM could save the flops or save the computations here. So here is a inference step of giving the input token BOS token, and we wanted to predict the and cat. So in the first step, we input the BOS token here, and we encode it into a local representation. And afterwards, we do the concept model, and then we got the concept. Because our concept model is training naturally with multiple token prediction. So in this part, so let's assume that our concept contains two token meanings, which is the and cat. And in the step 2, we got the output the, we run another loop. We input the BOS token and do the encoder, because our concept already has information about the cat. So we do not need any concept model inference in this part. So we can directly skip this kind of model inference and then do the decoding. So this is shown as 2 tokens into 1 concept. So imagine that because our concept model is most computation happens. So thinking about if our model could do the multiple token in 1 concept, for example 4 or 8, so it will increasingly decrease the inference cost during each inference steps here. So that's why our DLCM could save computations. So afterwards, because our model is quite new, so we need to some theoretical foundation to prove to get how to train our model and how to get the best model architectures here, and also the hyperparameters. So first, I will introduce the skin law here. So unlike the previous chinchilla law, which only contains the parameter is n, which is total parameters, d is the data volumes. So we also add a compression ratio. That's because the compression ratio controls how concept model reasoning granularity. So it's also very important for training performance, final training performance. And also we also need to take into account about the backbone allocation. So our optimization problem is that given this loss function with number of parameter, data volume, compression ratio, and proportion of the concept backbone, we could calculate what is the compute optimum model architectures. So here are some skin law derivation about the total compute cost. So instead of like Chinchilla law, so the cost is approximately equal to 6 times the number of tokens times the number of parameters times the data volume. We also add our concept flops, so which is also reduced by the ratio R. And for the second part would be the hyperparameter zero-shot hyperparameter transport. So in the past it's quite annoying. So when we wanted to get the best hyperparameters like the learning rate on a super big model, because you need to do something like this research on a really big model, and it's really expensive and with a lot of compute. So thanks for the mu p. So this kind of approach. We can train our hyperparameter on a very small proxy model. So we could use a research on this kind of proxy model. And once this proxy model is trained, we can perform direct transfer to the large concept model. So, however, our model is different from the previous. Also, our model is quite different from the standard LLMs. So we have different parts. So we have token module parts, which implies the encoder and the decoder module. And for the concept parts is our concept backbone. So as our experiments, we found that the token level module should not share the same learning rate as the concept backbones. So what we are doing is that we first use a grid search to find the optimal learning rate here for each module. And we try to see if all of these modules follows the mu p scaling strategies. So here is what we got the derivations. So for the token modules, so the learning rate eta is scales by the 1 divided by d, where d is the width of the encoder and decoder hidden dimension. And the concept model is also follows this laws, but it scales by the d that its own, so the hidden dimension is own. And for the embedding, which is the LM has, so it will not change. So you use a small model to train with this learning rate. For the bigger model, it will be constant. So here is the theoretical validations here. So let's look at the picture here. So this is mu p theoretical validation. So first we do the grid search and we find the optimal learning rate here. So which is in this point 100%, and then we scale it up to see if our mu p strategy could broadcast to the across different model sets. So what's our experiments is from the 87 million to 834 million model parameters. We found that in the 100% learning rate of optimal, with all loss is consistently the optimal, consistently the lowest. So that means that our this kind of decoupled or heterodical mu p strategy makes perfect sense. So secondly is the skin law fittings. So we test our skin law against the real world training runs. So in this chart, the right dashed lines represent our theoretical predictions. So the blue solid lines are the actual training loss. So as you can see, the models training from 274 million to the 833 million parameters. So the curves overlaps almost perfectly. So this high precision gives us some confidence to scale it up and investigate more computation into this model. So finally, is also the most importantly is the scalability. So does this architecture really save compute? What is the trend here? So you can see this plot that the trend is quite clear. So the advantage amplifies as the model grows. The x-axis is a baseline model size, and when we scale it up to the 1.3 billions, or it could achieve 40% of flop savings. So that's validate our promise. So our model could save some flops here. So finally, we train our model, with comparing to the baseline model to validate when it scale up if it performance good. So for the compression, we use RX4, and that means the sequence is reduced to 25%. And so that the attention complexity drops quadratically, and so from the OL square to the OL divided by 4 squares, and freeing up massive flops, and then we do the reinvestment. Because of this kind of flop saving, we can reallocate much more parameters into the concept models. So in the result, our model is 2.3 billions, and for the baseline model, which is llama like architecture, is 1.3 billions. So our model has in practice, our model has minus 34% flop savings, and we train our data on open source mixed data. So why we choose this kind of data instead of standard web EDU? That's because we wanted to test. This is a new architecture, and we want to test. So if different sources would affect the final model performance. So that's why we choose for part of our training corpus. So which is English web, Chinese web, code, and math. We wanted to say that this kind of diverse mix to ensure the robust concept formation, so across different domains. So for our evaluations, we do the 12 benchmarks, zero-shot benchmarks. And here is the final performance. So overall, we can see that there is 2.69% improvement on average. And we performance good on the multi-choice general knowledge, and also in the cultural and multilingual knowledge. But I have to be transparent that this kind of red number, specifically the Bool Q and Reese Q. So why does this drops? So it comes back to the fundamental nature of compression. So compression implies loss. So if you look at the nature of these benchmarks, so Bool Q and Reese, they heavily focus on the fine-grained text understanding. They often ask you to find a date, a name, or some adjective, so within a very long context. So because your model comprises a lot of tokens into code concept, so kind of like we are treating off the resolution to the high level reasoning, because all of these surface details will easily be smoothed out when we do the concept compression. So, but we are believing that, so if we do more trainings, those model will preserve those critical details. Because as we observe our training loss, we found that at first usually our models has a bigger loss comparing to the baseline model, but afterwards it will decrease faster than the baseline model. So that's why we are believing of that. So all in all, so conceptually, so DLCM split two questions. So first is what to think. So we handled with boundary detection. So second one is how to think. We move from the token level reasoning to the concept level reasoning. So this decoupling enables adaptive compute allocations. So finally, I want to represent why our DLCM works. So why we save so many computations, but our performance is better than the baseline model. So here is where it happens. So if you look at the x-axis, so with 0 to 18, so it represents the relative position within concept. So if this is 0, it means it's a boundary. So if this is 1, it's a token that's next to the boundary. So what we are doing that we wanted to check the probability, which means that if the model are confident to this token, so we can see that the green bar is all on a concept model wins, and the red bar on the baseline model wins. Although the baseline model has a lot of wins, but it usually appear in the quite confidence tokens, so they are not difficult. So our model usually wins in the difficult tokens. So that's why this model allocate more compute into difficult tokens, because our training is naturally want our concept to concentrate on this critical moment or significant shift. So that's why our model is more efficient. And finally, we wanted to show that our dynamic segmentation makes sense. So here is a Python code that, so if this boundary aligns the human cognitions, so what we are doing is that we given this kind of 87 tokens Python code, and we want to try to see that if all of this speed make perfect sense. But you can see that import touch and from touch utils data import data side and data loader. So we are happy to see that without any explicit supervision, our model could perfectly align the humans' combinations. So that means that for the mathematical derivation, so the human combination and our model are doing the similar thing. They are using the information to cut different kind of concept in our mind, also in our models. So finally, here is some limitations on the future direction for models. Because our model architecture right now is quite new, and we still have some limitations. The first one is that our compression ratio is fixed. So during training, you need to set a static target ratio, but this ratio cannot be changed during the inference. So future work could explore more about how to do this kind of dynamic content adaptive compression rate. The second one would be the high VRAM usage. So because our model is 2.3 billion parameters, but for the standard our baseline model is 1.3 billion parameters. So that means that low flops not equals to the low memory cost. So that means for the inference cost, although we save the flops, but we have some trade-offs here. So maybe in the future direction, we could solve kind of this kind of problem. So first one would be okay, and then I will introduce about something about the future direction. So first, that very intuitively is that we could apply some multimodal concept into our structures. And the second one and the second and third one is trying to solve the problem that the limitations that we present here. So because our models use more parameters in order to achieve similar performance, although it's already computational saving. But what we can do that if we could apply our concept model into MOE structures, so we keep the total parameters here, but increase the activation parameters. So that means we did not waste any kind of rewraps during the inference, and we also saved a lot of flops. I think the second thing would be, so we keep the same parameters. If we could use kind of like some adaptive depths or parameter sharing strategies to increase the flops during the concept model reasoning, instead of just simply add the parameters. So some method like the universal transformer and something looped transformer, kind of like these things could be a potential direction to investigate. So here is the conclusion, and the final one is that our paradigm shifted the token level processing to the concept level reasoning. So our contribution is that we first design this kind of brand new dynamic structures that all the boundaries are learned from data, and we reasoning in this kind of concept-based space. And afterwards, we design the scaling law and decoupled mu p to tell everyone how to train our model efficiently, what is the optimal structure of our models. And the third one is that we prove our efficiency with both in performance and flops. So thanks everyone. Yeah, that's all.
Okay, thank you very much for this very interesting talk. So I do notice that recently latent reasoning has become like very popular in both language model and vision language model. So I wonder, so because in your talk you mentioned, okay, we have improved efficiency, we have improved the performance a little bit as well. Do you think the motivation of doing this latent reasoning is mainly because it aligns with the human intuition about like how our brain works more, or you are thinking you believe that this is the new architecture that can lead to a more promising foundation model?
I prefer the second explanation. So this could be a more efficient foundation models. So because right now during the deployment, our biggest challenge is that the model is so big, and for the inference, we offer we offer a lot of token to the users, and so we need to speed up our inference times. So there are a lot of strategies that, like the speculative decoding, they use a small model to decode it first, and they use a large model to verify that. So it seems like our model could make all of these small model inside use the concept way. So I think this could improve the coherence and solve a lot of deployment problem about that. But right now, in this period, there are still some limitations here because our model add a lot of parameters. So probably apply some two future direction. So first one would be like MOE or some other parameter sharing strategies. There could be a trend that this would be a foundation model structures. Yeah.
I see. Okay. And so for now, I wonder, the model size you show are like, so it reminds me of the BERT model size, like 200 million or like 800 million. So I wonder, what can you expect to be some difficulty or like bottleneck when we do actually scaling up? Like if we want to scale up to like 0B or like several hundred B model parameters, what you would expect to be the bottleneck?
It's a really good question. So actually, we are already do some scaling up. We did not find too much
difficulty.
Yeah, right now, because we designed this scaling law and found that it follows the scaling law. We definitely train bigger models, larger than 1.3 billions, and probably our model is not big enough. Like OpenAI model that is, I remember 200 or 300 billions, probably. I'm not sure. So at that big, because we don't have too much computations here. So probably right now I did not see too much difficulties. Yeah, it's perfect. Follow the scaling law. Yeah.
I see. And for now, like, what do you think could be the next step of improving, say, not efficiency, but like improving the performance of this latent reasoning, or like the concept learning language model? Like, what do you think is like? Because I think you mentioned, like, say we can do adaptive layer or like early exit. Then performance-wise, what do you think can be the key?
Okay, for the so right now I think there are a lot of strategies about this part. For the pre-training, I think most of these are focusing on the memorizing. I think quite a lot of works are doing this decently. I think a lot of these could have some facing the problem that the compression. So this kind of part. So, but it's increase the efficiency, but decrease the performance. But I think but I think for the in the product or the view, so perspective, I think probably the most important thing is how to use this kind of latent reasoning into the reinforcement learning part, and I think that one would be the most difficult. Yeah, that's my point. So for the performance, I think the key to improve that is that how to be against this kind of compression loss to eliminate that, to make it more. Right now, I do not have a bad idea about this part, but I think this is the key to solve these kind of things.
I see. Okay. So you mentioned two point. One is like how to train an RL based on this foundation model, and the second is how to for the compression loss, like how to decrease the compression, like how to make how to do the compression better.
Yeah.
Okay. And also, like, it kind of remind me because say now in our large language model, a lot of recipe and infra are like very like kind of mature. I wouldn't say like very mature, but like reasonably mature. Like how you serve those language model in inference time, how you train them, like the training infra, and how you do like all the RL, and like we have some, like, for example, like VERL, etc. Like how you do such RL and etc. But then for this, and there was like a lot of infra that's trying to accelerate, that tries to accelerate the implementation. So I wonder, for example, like for this model, does it naturally, for example, fit into VLM or SGLang in serving time? And for RL, what's the issue? Is it because it's not because of the rollout, or is it because like how you, like which part you think is like stopping RL to function properly on your model? So like two questions.
Okay, I got it. So for the first part is infra things. So I have seen a paper that tells that the settings of the infra is depending on the granularity about the your token, because you have a communication constraint there. So because our model has this kind of concept level, which is a high level granularity. So I think the setting is there, because but I'm not an expert in the infra. Probably this would help the infra to accelerate more. Yeah, that's the first thing. And for the reinforcement learning, so I think this is a really interesting question, because right now latent reasoning is not widely used in our product. That's because the latent space is really hard to be controlled. So RL is that kind of you do some like a rollout and then you comparing about the final results and to get the reward and refine all of them. But how to roll out, have some good rollout in the latent space? This is opening research questions. So because for the token latent space is quite, I would say, decisive. So you, considering you have 1,000 dimension of the hidden embeddings, so each of the position moves in different direction. So it will consider into a direction. But if this direction in the high space, high level dimensions, so it's would be very critical. Our results right now are focusing on the token level, right? So the token level is a low dimension, so it's quite fixed. All the results looks perfect, makes sense. So you see the good result here. But currently in the latent reasoning, it's really in the high dimension. It's really easy to fall into different pitfalls that could be meaningless, could be not usable. So probably this is the most important part for the RL training if you wanted to do the latent reasoning. Yeah.
I see. So it's mostly in the rollout part.
Yeah. I think, yeah, that's my opinion.
Okay, cool. Yeah, let me see if there are other questions. Okay. Okay. For now, I am not seeing like other new questions. Yeah. So. Okay, so I think that's all for today's talk. Thank you very much for Xingwei to give us this very interesting new direction to think about. And there do seems to be like a lot of potential directions that you can do to improve, to extend this like dynamic concept learning, latent reasoning language model. Yeah, so this all sounds very cool, and thank you for your talk, and thank you for your time, Xingwei, and thank you for all our audience and for the discussion. Okay, yeah, so I think that's all for today now.
Thank you for your invitation. Yeah.